are at government positions. Also, some of them have established their multinational companies. The university has started many skill-based education and various departments offering multidimensional course program for the betterment of students. In the context of modern sciences, as Sir has already told, partial differential equation form an integral part. Many physical phenomena can be modeled by the set of governing equations, and several of them being partial differential equations. So these can be applicable in many branches of sciences like quantum mechanics, astrophysics, biology, environmental science, etc. In today's webinar, both of the resource persons will address the recent developments in partial differential equations and will also discuss the challenges in this topic. I expect that the deliberations in this webinar will be fruitful and beneficial for the PG students and research students. Once again, I welcome you, sir, and best wishes for the success of seminar. Thank you. Thank you very much.
Thank you, sir, for your valuable guidance. You are actually the motivation behind organizing such a kind of national webinars. Without your support, it could not be possible for us to organize these types of activities. Thank you so much, sir. Now I request Mr. Vinay Kamli, sir, to put a vote of thanks for the inauguration function. Kamli, sir.
Okay, ma'am. First of all, I am very thankful to our University Vice Chancellor, Fernandez ma'am, to organize this function, to give the permission to organize this function. Then I would like to thank our director of school, Mr. Gutesh sir, to giving the permission to organize such a program. And also I would like to thank Mr. Dr. Suman Kumar sir to giving the time for this webinar. And also I would like to thank all the students and participants here and our faculty member to join to giving the time for this function. So thank you, ma'am.
Okay, sir.
So I would like to request Mr. Suman Kumar sir to start the session. Thank you.
So shall we start immediately?
It's up to you. If you want to start immediately, we'll start. Otherwise, we can start at 11:30. It's up to you. Completely.
We will start, sir. Otherwise, it will be a break and participants may leave and again they will take time to join.
Okay. Fine. We'll join. In 3-4 minutes, I'll
Yes, sir.
open this and start sharing the screen.
Yeah, okay.
Let me share the screen. Yeah. Yeah, first of all, I would like to ask how many research scholars are there in this meeting?
Some 2-3 research scholars are there,
Two,
sir.
three, not many. Okay, most of them are MSc. Okay, MSc
Okay.
students. Okay,
Yes,
fine.
yes.
Yeah. To begin with, I want to ask you, can somebody define what is a surface?
Actually, participants are requested to have a communication with Dr. Suman Kumar, sir. As he has told us earlier, it should not be a one-way communication.
Yeah. See, you can say something which may not be correct. I don't mind. You should not inhibition saying wrong things, because without making mistakes, we can't learn. Yeah. Can somebody say what is a surface, or at least mathematically? What's a curve? At least you say roughly what is a curve. It need not be very precise.
So someone has given a
The extension of the plane.
chat.
Yeah, then you have to tell what is a plane. Mathematically, what is a plane?
Mandar, instead of putting the message, you can unmute yourself and
Yeah, you can tell. Can tell. Well, let's have discussion like this.
Yes.
Mathematically, what are these two objects? Because we are going to deal with geometry now, so we should know what are curves and surfaces. How do they look like mathematically? But geometrically, you know what is a curve? It's like a wire, okay, bent in some arbitrary shape. Okay. Suppose if I show you a wire which is bent and asked you whether it's a surface, you will say that no, it's not a surface. I know that you know up to that level. Suppose if I show a paper like this and say whether it's a curve, you will say that it's not a curve. But mathematically, what is it? Yeah. Okay, maybe it's you in bit shy. I will keep asking this kind of questions. You answer maybe later also. I'll give you answer now. Mathematically, you have a continuous map from the interval I to R2. Okay, so T going to x of t, y of t.
सर मध्ये बोलले तर तुम्ही बोला आणि अगदीच विचारलं तर सांगा शी हॅज सम अर्जंट वर्क अँड शी विल बी बॅक इन 15 minutes असं म्हणा. ओके.
one interval, you have two intervals, I1 and I2. And suppose you have a function R3. So what is it? Suppose you have these two parameters. Maybe you can put S and tau. Okay. And you have three functions involved: x of S tau, y of S tau, z of S tau. Okay. This denotes surface. And this S and tau, they are called parameters again. This and this, they are together, they are called parameters. Okay. This is surface. Of course, the condition is this has to be, C1. If it is not C1, you have if it is just a continuous function, you may have a surface like this, a sharp thing. It's a plane like this. You don't have continuity, differentiability along this edge. You have a plane, and you have another plane like this. Okay, both of them are intersecting along this line, and along this line, differentiability is lost. Okay, but I don't consider such surfaces. Okay, I consider only this kind. Okay, so they are called. This is called parametric form of surface in R3. Okay, this is parametric form of a curve in R3. Okay, now I have a different notion of a curve on surface. Different definition I can give. What I can do is, suppose f is a function from let's say R to R. Okay, you take C1 function. See, as in my lecture, I will not worry R sufficient number of times differentiate. Okay, I will not. What happens if it is only C1 but not C2? No, I don't care about such questions. I assume for time being that all the functions that I'm based on the context. Okay, it's sufficiently smooth. Okay, and you consider this f of xy is equal to constant. So what does it say geometrically? What is this f of xy is equal to constant? In order to understand this geometrically, you go to three-dimensional picture. Okay. So this is x-axis,
MCA ऊपर है फर्स्ट फ्लोर पे
z-axis.
RS मेंते सर का ऑफिस में
Okay.
मेंते
And then you have this. You draw z is equal to f of xy. You draw z is equal to f of xy. So what will be z equal to f of xy? It is some curve like some surface like this, isn't it? X and y are varying over R2. Okay, and you draw z is equal to f of xy. As f is a given function. And then what are you doing? You are considering set of all x and y such that f of xy is equal to c. Okay? So what does it mean? I am chopping this surface with a plane. Okay? With a plane I am just chopping this surface. If I cut the surface with a plane, what do you get? Intersection of a surface and plane. What is it? It is a curve. You imagine any surface and then cut it with a plane. Of course, sometimes you can have more curves also. Suppose you imagine a kind of surface which is waves, and then you cut at a point, cut it by a plane, then you get different curves. Okay, you get different curves. So there is a way of defining curve in this using function of two variables also. Earlier we have seen defining the curve, how to define curve using parameter. Now I am using another method to define a curve, that is called level sets. Level sets means I have a function of two variables. I am looking at the intersection of the plane z is equal to c and the surface f of x. Okay, z is equal to f of x. So intersection of these two, a plane and this, the surface, this is called the level set. Okay. So I am identifying curve as a level set. By the way, how can I identify plane as a, how can I identify surface as level set? It is because of a result called implicit function theorem. Okay. That's something called implicit function theorem. We'll quickly recall what it is. It's implicit function theorem. Use it in a different color. Of course, this is not something special to two-dimensional thing. It is in general true for any n dimensions. We'll quickly see how to use implicit function theorem for to identify surface as a level set. Okay. So implicit function theorem, I will not state it completely, but I will give you an idea of what it is. Okay. You take the simplest possible case, R2 to R, this f from R2 or omega subset of this is an open set, R2 to R, okay, xy going to f of xy, okay. You take a C1 function, and assume that fy at x0 y0 is non-zero. Okay, I assume that fy is non-zero. Then there exist two neighborhoods. Okay, one neighborhood around x0 and another neighborhood around this point x0 y0. Okay, such that the following holds. Okay, of course, two neighborhoods, and there exists a function. Maybe you call it as h from vx0 to r. Okay, such that I can write y in terms of x. That is, f of x, h of x is identically equal to f of x0 y0. Okay. In other words, I have a new function h of x, which is implicitly given by this relation f of xy is equal to f of x0 y0. That means I have this. You just chop with this you just chop with this plane. Z is equal to x naught, f of x naught, y naught. Okay, this is f of x naught, y naught. You just chop with this plane. Z is equal to f of x naught, y naught. Whatever you get is a curve locally. Okay, what is that curve? It is x comma h of x. It's a one parameter thing, one parameter object, right? Instead of t, I have x. Instead of y of t, I have h of x. Okay. Of course, here if f is C1, then this is also C1. If f is C10, then h is also C10. Okay. And second is if this is true for every x in this neighborhood. This is the most important feature. This is the most important feature. And the other thing is it's a standard thing. H of if f of xy is equal to f of x naught y naught, for some xy in W implies y is equal to h of x. In other words, this level set is precisely given by the graph of the function h. Okay. By the way, what is the graph of a function? I am using another geometric notion. What is the graph of a function? Definition. Suppose G is a map from, let's say, an interval to R, and I am taking the simplest possible cases. I am not doing things at more generality, doing simpler things so that you understand it clearly. Okay, I is an interval. Suppose G, you take a continuous map, I to R, a continuous. I would say the graph of G is this set of all x comma y such that y is equal to g of x. Suppose function is given to you and the graph is nothing but it's an object in R2. Suppose this is y is equal to g of x. All this set of points in R2 where x belongs to I and y is equal to g of x, they are called this set of all points, they constitute graph of G. Okay. And similarly, I can think of a graph of any function which is defined on any domain, need not be an interval. For example, you take, earlier you have taken z is equal to f of x, xy. This is nothing but graph of f. What is graph of f here? Graph of f equal to set of all x, y, z, okay, such that z is equal to f of x. If the domain is in R2, then graph of f will be in R3. Okay, whereas here the domain is in it is in R, then graph of G is an object in R2, one dimension extra you have to take. Okay. Now, if I use implicit function theorem and use the same thing that I have used for curves, okay, what do I get for surface? Instead of R2, you take R3. Okay, then you have f of x, y, z. You take one coordinate. You take the partial derivative of f with respect to any coordinate being non-zero. Okay, then that coordinate can be replaced with a function of other coordinates. Okay, so what is implicit function theorem? From, let's say, omega subset of R3 to R. How do I do that? You have f of x, y, z going to this. Suppose fz at x0, y0, z0 is non-zero. This is the most important thing. Then what can be done? This z coordinate can be replaced with other two, a function of another two coordinates. Then you have h of x comma y is equal to, suppose you assume that for simplicity, you assume that f of x0, y0, z0 is equal to 0. Okay, then this is also the 0. If it is 5, then you have this is equal to 5. Maybe I simply do like this. I just don't care about this. This is also fine. So essentially, this condition is giving me that there exists a function z is equal to h of xy locally. Locally. Why I said locally? Because the condition says there exist two neighborhoods. One around x0, another one is around x0, y0. Okay. So therefore, all the results that we obtain using implicit function theorem, they are valid only locally. Okay. So this is valid locally. So this is another way of defining surface as graph of a function. Okay, so you have this neighborhood around x0, y0. You have two neighborhoods, right? One around x0, y0, and another one around x0, y0, z0. So there exists a neighborhood around x0, y0 such that in this neighborhood we have a surface like this. Okay, this is what z is equal to h of x. Okay, so these are the geometric things that you need. Of course, there is nothing great about z. If fx is non-zero, then what do you have? Then x can be replaced with other coordinates. What does it mean? Then there exists h, which is a function of y comma z, such that this holds f of x0, y0, z0. Okay, if fx is non-zero. Suppose if fy is non-zero, then this y coordinate can be written in terms of other two coordinates. So this is if fy at x0, y0, z0 is non-zero, then this y coordinate can be replaced with other two coordinates, a function of other two coordinates. H of xz comma z is equal to f of x0, y0, z0. For every xz belongs to this neighborhood. Okay. So this is implicit function theorem. Here, special case. Of course, in your analysis course, you might learn it in more generic way, but you should understand the geometry behind it. Okay. You have a level set, and then I am cutting with a hyperplane. So I'm just cutting with the hyperplane. Then you have curves, whatever left out are curves. You identify those curves as graph of H. You see, this is graph of H. F of xy is equal to f of x naught y naught is precisely the graph of H. Okay. So with this basic introduction, I move on to formulation of Pd. This is what Jyoti was asking me to do it. Formulation of Pd. Okay. You suppose phi is a function of x, y, z. Okay. Psi is a function of x, y, z. These two functions are given. Okay. We want to find a PDE for which f of p psi is equal to 0 is a solution. Yeah. Now I want to ask you two things here. Suppose you have a PDE. You take ux plus uy is equal to 0. We have a PDE. Right? And can you say that u of x, x comma y is equal to x minus y is a solution of this PDE? Can you say that? The solution of this is, can you say that?
Yes.
Yes?
Yes, sir.
Why?
Because if we to LHS equal to RHS.
No, you're almost correct, but yeah, formulation is formulation you have to do carefully. Yeah. See, here I have ux plus uy equal to 0. This is equation. This is equation. For example, when you take u is equal to sin x, this turns out to, you substitute u equal to sin x in this equation, you get a false statement. Okay, that's what I mean by this doesn't hold. When you put u equal to sin x simply, then what you get? You get this cos x is equal to 0. For example, you take u equal to sin x for x between, let's say, 0 to pi by 4, or 0 to pi by 4. Then cos x will never be 0 in 0 to pi by 4. No? You get a false statement. This doesn't hold. False. Okay. So this is an equation. First you understand the difference between equation and identity. This is very important. equation and identity. Equation means something like this, or an equation that you have already seen before. Means for some values it may hold true, and for some values it may not hold true. For example, when you put x equal to 5, this is a false statement. When you take x equal to minus half, it's a true statement. Okay. And for some values it may hold true or not, that I don't know, but certainly for some values it may not hold true. Such a thing is equation. What is identity? It is something like this: x square plus 2x plus 1. This is an identity. That means no matter what value of x you substitute, this holds. But according to context, for example, here I cannot substitute something which doesn't commute with 1. But let us take what we work in a real number system. This is an identity. That means it holds for all the values of the variables under discussion. Okay. So here, when you substitute u of xy equal to x minus y here in this equation, then you get 0 is equal to 0, which is an identity. So equation is becoming identity. Okay. So that's what you mean by solution. So you have a PD in your hand. When do you say a function of two variables is a solution? Suppose you have a PD like this: xy, u of xy, ux of xy, uy of xy. You take the simplest form of PDE in two variables. The same thing can be done for n variables without any difficulty, but let us this should be identical. I put 3 equal to symbols. It should hold for every xy in the domain of the P. Okay. Or in a neighborhood of an initial curve when we discuss Cauchy problem. First you understand the definition of solution. But sometimes in your PDE course you would have seen that a function of xyz is also a solution. It is because you are using the implicit function theorem indirectly. Okay. We say that a function of xyz is equal to C is a solution of, okay, you call it as this is a PDE, okay, first order PDE, okay. We say that phi is a solution of PDE if this happens. Okay. Moreover, we say that this capital F of xyz equal to C is a solution of PDE. Okay. If what should happen? First, you should be able to write z in terms of other two coordinates. When is it possible? When can you write z in terms of other two coordinates? Hmm? Answer is here. If the derivative with respect to the third variable, if it is non-zero, then I can write z in terms of other two coordinates locally. Okay? We say that f of xyz equal to c is a solution of PDE if, number one, what should happen? Fz, derivative of f with respect to the third variable, okay, is non-zero. And number two, if it is non-zero, what happens from implicit function theorem? From the implicit function theorem, what happens? The implicit function given by this f, what is it? H of xy, right? H of xy, it satisfies, or satisfies means we such that this f of xy, h of xy equal to c, whatever c, the same c, implicit function theorem, the implicit function h has the property that you substitute in the place of unknown u this function h. Okay. In the place of the unknown u, you simply substitute h, you get an identity. Okay. This holds for every x and y in this domain. Okay. So these two are the definitions of solutions. One is a solution given explicitly in terms of function of x and y. Another one is solution given implicitly. Okay. In that case, this f of x, y, z equal to c is called the integral surface. Okay. So this is another definition. Integral surface. Z is equal to phi of xy. If the solution is given implicitly, then simply f of xyz equal to constant. Either this or this. Both of them are called integral surfaces. Though you have f of xyz equal to c, of course this fz has to be non-zero. If fz is non-zero, then anyhow z can be written in terms of this is a surface. Z can be written in terms of other two variables. This is that graph. Locally, this is a graph of the function h, and maybe graph of the function u. Okay. So similarly, when I say f of function of xyz is equal to 0 is a solution, what does it mean? It means that f phi is non-zero or f psi is non-zero. Okay. Apart from this, I want derivative of phi with respect to the third variable or derivative of psi with respect to the third variable is non-zero. Okay, so that when I take derivative with respect to z, this is a function of x, y, z, right? Total, it's a function of x, y, z. When the derivative with respect to the third coordinate is non-zero, then I can write the third coordinate in terms of x and y. That function is the solution. That function of two variables is the solution. Okay. Yeah. Now, my interest is to find the PDE for which f of phi psi equal to 0 is the solution. Okay. So these are the basic assumptions. Okay. This is the objective. We want to find PD for which there is a solution. And how do we achieve this objective? Let u be the function given by f of phi psi equal to 0 locally. Okay. What does that mean? U be the function given by means what? F of, actually you should have a x, y, z, but instead of z I have u of x, y. Okay, z can be written in terms of other two variables. Okay, that's my assumption. Assumption of implicit function theorem holds. Okay, so psi of x, y, u of x, y, this is an identity. Okay, this holds for every x, y in the domain of our discussion. Okay. In fact, since it's locally, it is possible. So you take, there exists some open set where this holds. Okay. Since it's an identity in x and y, I can differentiate identities in x and y. Okay. For example, if I differentiate this identity with respect to x, what do I get? First, x is there in how many places? First you identify that x is here, x is here, x is here, and x is here. There are 4 places in which x is there. Okay, therefore you have 4 terms. So first, how do I enter this place? Yeah, I have to differentiate f with respect to first variable, that is f phi, and then phi x. And then how do I reach this place? F phi, first I enter this, just chain rule, and then phi has to be differentiated with respect to third variable, phi z, and then once I reach third variable, that means u of xy, this is ux. This is how you reach x, which is here. And then how do I reach this x? F psi, psi x. And by the way, how do I reach this? In the same way, f psi, psi z, and u x. This is an identity. And similarly, differentiate this with respect to x. And then here, with respect to y, if you differentiate, what do I get? Where is y? Y is here, 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 and here. So f phi y plus f phi z uy f psi y f psi z uy is identical equal to 0. Okay? Yeah. Now you write everything in matrix form. What do I get? Simply take phi x plus phi z ux. Okay? And this is psi x, psi z ux, phi y, phi z uy, psi y, psi z uy, f phi, f psi. Okay, and from your assumption, this f phi is never 0 and f psi is never ideal. One of them has to be always non-zero. In the sense that this cannot be a 0, 0 vector in R2. Okay, so you have a system of equations Ax equal to 0 and x is non-zero. Implies what? From these two, I conclude that determinant of A is 0, isn't it? So determinant of this object, this matrix, is 0. Determinant of this is 0. You just simplify this, well, cross multiply, you just evaluate the determinant, then you end up getting, and I'm straight away writing the final answer. That's a beautiful way of writing it. Phi psi, maybe let me use phi psi. Yz ux plus phi psi yz zx. We have this cyclic expression is equal to phi psi xy. Okay. And here, what is this notation? Where phi psi, it's a standard Jacobian. What is it? Phi y psi x minus phi x psi. Okay. Of course, similarly, you take you get these other expressions. Okay. So this is very surprisingly, we observe this carefully. This is a quasi-linear Pd because you have this z. This phi is a function of x, y, u, because that's how you have written, right? Z is written in terms of u. Sorry, z is written as a function of x and y. Okay. So this phi, this expression has u inside it. This expression also has u inside it. But derivatives of u, they don't have any nonlinear terms, in the sense that the equation doesn't contain any nonlinear part of derivatives of u. That's why this is called, it's a quasi-linear equation. Okay. Typically, what is a quasi-linear equation? P of x y u ux plus q of x y u uy is equal to r of x y u. Okay. So this is a standard form of quasi-linear equation. Of course, we assume that PQR never vanishes simultaneously. This triplet, it never vanishes. Okay, so this is quasi-linear equation. Now let's try to understand the geometry of it. Okay, geometry of this quasi-linear equation. First of all, this u is a solution, right? That's what you are taking. U is a solution of this PD. Why u is a solution of this PD? Always I am having identities. This is also identical 0. This is identical 0. What does it mean? It actually means that u is a solution of this quasi-linear PD. Okay. Yeah. Now consider this quasi-linear PD. Okay. Consider this quasi-linear PD. Suppose z is equal to u of xy be an integral surface. That means, of course, u is a solution of this, and I am just considering this. This is just a surface. What is it? This is given by z is equal to u of xy. Yeah. Now, observe carefully. You take any point here on this surface. This is z axis. You take any point on this surface. Then, what is the normal to the surface? Can somebody tell me what is the normal to the surface f of x, y, z equal to c? Just you would have learned, no, in your BSc. Normal to the surface? No? Okay. If you have not learned, I will tell you. Gradient of f gradient of f is a normal to the surface. It's a vector, right? Gradient means what? Fx, Fy, of course at the same point, and Fz. Okay, this is a normal. Now, for this, what is a normal? For this surface, in the place of f, what you have? Z minus u of xy is equal to 0. You just compare. In the place of f, you have this expression. In the place of c, you have 0. So, what is the normal to this surface? Z equal to this. You have to take gradient, no? It's like minus ux for this expression. You consider this as capital F. Fx is what? Fx is nothing but minus ux. Fy is minus uy. Fz is 1. This is the direction of normal. Okay? See, this basic geometry is something that is needed to understand this PDEs. Okay, so this is a out normal. Okay, so what is it? Ux uy minus 1. Yeah, of course, earlier you have this minus ux minus uy 1. If this vector is normal, then minus of this vector is also normal. Of course, one will be pointing outward, upwards, and another one will be pointing downwards. Okay. Yeah. This is this outward run. Let's take this normal is in this direction. What is this equation telling you? Equation is telling you that I can write the equation in like this: P Q R dot product with Ux Uy minus 1 equal to 0. Isn't it? I write this equation in this way. In other words, this is a normal, ux uy minus 1 is a normal, and pqr is orthogonal to the normal. Say dot product of two vectors is 0. That means what? One is orthogonal to another, right? So therefore pqr is perpendicular to ux uy minus 1. Okay. So what do you mean by this? PQR is perpendicular to the normal. It is normal to the normal, isn't it? It is orthogonal to the normal. So therefore, where should this PQR direction, where should it be? You have a surface, you have a normal to it, and you have a vector which is normal to this normal. So where should this PQR lie?
On the surface.
Huh? It should be in?
Surface.
No, it cannot be in surface, no? Normal to, suppose you take sphere, simplest possible cases, you take sphere. You take north pole, okay? Something which is, you take the sphere like this. This is the north pole. You take normal, upwards, and you take a vector which is perpendicular to this normal. Where will it be? Will it be on the sphere? It will be on the tangent plane of the sphere. Okay. Suppose you put a tangent, you put a plate or a plane on the sphere, at the north pole. It should be in the tangent plane. Okay. Right. So therefore, PQR, a line with direction ratios PQR, lies in the tangent plane. You are very close to the answer, but instead of saying on the surface, if you had said it lies on the tangent plane of the surface, it would have been excellent. But very good. I appreciate you. Okay. So therefore, a line with DRs, direction ratios, PQR, lies on the tangent plane of the integral surface. Right. So you take a tangent plane at this point, okay, and this tangent plane contains a line with direction ratios PQR. Always, no matter what point you take on the surface, integral surface, always this tangent plane contains a line with these things. That gives me a method of devising the solution. Okay, see, this is where this is a fantastic observation made by Lagrange. Okay, so what he did was, okay, I know that if there is an integral surface, it has this property. But how to find this integral surface with these properties? How to find solution for this? What I know is, if there is a point on an integral surface, then at that point, for that integral surface, there should be a line in the with the direction ratios PQR in the tangent plane. It should lie on the tangent plane of the integral surface. So what he did was brilliant thing that he has done. Okay. So you take this I don't know what is this S, what is the solution surface, I don't know. Suppose there is a point on the solution surface, integral surface. Okay, then this on the tangent, suppose this is a surface. You just take a surface, and this surface has a tangent plane attached to it, and then you have a vector. You have a line with the VR's PQR. So from this, what you can conclude is there exists a curve. There exists a curve lying on this surface completely. There exists a curve that lies completely on this surface, such that for this curve, tangent direction is PQR. So that means what he has done is he has isolated this part. One curve he has just taken from a surface and said that this curve should have tangent direction PQR. Okay. C lies on the integral surface. Okay. Direction of C is PQR. This is observation. Okay. There exists a curve. There exists C. There exists curve C. Okay. That lies on the integral surface, and directions of C is PQR. This is a simpler observation, which is extremely crucial. First, I simply wrote this thing. First observation is line with dr's PQR lies on the tangent plane of the integral surface. From tangent plane, since I see all the vectors in the tangent plane are spanned by the tangent lines of the curves. Okay, so therefore there exists a curve that lies on this integral surface, and direction of C is PQR. So, in other words, there exists curve in C means what? Curve in R3 means what? There exists a curve like this, P of X of S, Y of S, Z of S. Okay, maybe I will just remove this and then push this further. Okay. Dy by ds is equal to Q of X of S, Y of S, Z of S, and what is the third one? Dz by ds is equal to X of S, Y of S, Z of S. Okay, so these are called characteristic curves. Okay, so from this simple geometry, what one can do is, since there exists a curve C that lies completely on the integral surface with the directions given by PQR, you find this curve X of S, Y of S, Z of S. You solve this. So certainly this X of S, Y of S, Z of S from geometry, what is clear? What is this? What is clear from the geometry? This belongs to the integral surface. Belongs to this, in other words, solution surface. Okay. Of course, whatever I am telling you using heuristic argument, using geometry, one needs to prove. Okay. And by the way, what is the guarantee that this system of equations admits solution? What is the guarantee? Is there any theorem which assures a system of equation, system of ODEs has solution? Is there any theorem which guarantees system of system of ODEs admit solution? Have you heard of Picard's existence theorem? Cauchy-Lipschitz existence theorem? No? Okay. So maybe later on you will study them. Yeah. So if PQR are smooth, then locally solution exists for this system of equations. By the way, the same thing, same system of equation, Lagrange has written it in a very beautiful way. It is this: dy by q is equal to dz by r. I think this you would have seen in your Pde course. Okay, dx by p. This is a shorthand notation of whatever I have written so far. Characteristic curves. Okay, Lagrange used this, and ever since people are also using this with the use of notation. Okay, those days people were using these kind of expressions. Of course, now it is not a very good idea to use these kind of expressions, because dx, dy, they have some different meaning. Okay. So So a method is developed and to find curves on the integral surface. These curves are precisely ODEs. So in this process, what did we achieve? We achieved two things. One is number one, we found curves on the integral surface. Instead of finding integral surface, z is equal to u of xy, this is what we are supposed to find, but we found curves, not full surface. Second, in this process, what did we do? We found the relation between ODE and PDE. So PDE is, given PDE, became system of ODEs, okay, along the characteristic curves. Okay. And still the last thing that that we need to do is how to form surface out of curves. How to form surface out of curves. It's something like a weaving process. How does weavers weave it? For example, you consider the Cauchy problem. Okay. In Cauchy problem, what we do? We need to find the integral surface, an integral surface. An integral surface z is equal to u of xy, okay, which contains the given curve. Curve means it's with some parameter, x of tau, y of tau, z of tau. Okay. So in this problem, what we need to do is we need to find an integral surface such that contains a given curve. For example, this is a curve. This is a curve in R3. Okay. X of tau, y of tau, z of tau. But what I know is the integral surface contains a curve C with these directions. Okay. Dx by ds equal to p, dy by ds equal to q, dz by ds equal to r. So what I do is I start with this initial point. I start with a point which is on this initial curve, and I solve this system of characteristic equations. Okay. Then what happens? I get a curve which contains this curve, certainly contains this point. Okay. And then I fix another point and I find a curve, a solution of characteristic equation which contains this point. So suppose if I find curves like this, okay, and from every point on the initial curve, from every point on the initial curve, suppose a characteristic curve is coming out of it. See, any solution of this is called characteristic curves. I told you. These are called characteristic equations, this set of equations, and solution is called characteristic curve. Okay, that's what I have. Okay. Through every point there is a curve coming out of it. Okay. Through every point there is every point on this initial curve, a characteristic curve coming out of it. Suppose this is the case. Okay. Tell me, suppose if you form a surface out of these characteristic curves, will that characteristic curve, repeat this. Suppose through every point on this initial curve, a characteristic curve comes out. Okay. And you form a surface out of characteristic curves. Okay. Now tell me whether this initial curve, this is called initial curve, whether this initial curve lies on integral surface or not, tell me.
Yes, it will.
Is it automatic?
Yes, sir.
Yeah, it's automatic. I want others also to get convinced. Suppose there is an initial curve like this, initial curve. Through every point on the initial curve, there is a characteristic curve emanating. Okay, you have a curve like this. Through every point, a curve is coming out, and you form a surface out of it. Does this initial curve lie on this surface or not? It lies on the surface. So this is a beautiful geometry involved. Okay. So what is the method of finding solution of Cauchy problem? So step 1, solve characteristic equations with this is characteristic equation, no? Maybe you say you define this as some star, system of equations star, characteristic equations star with initial data x of tau, y of tau, z of tau. That means I fix tau, that means I fix a point, and then I solve it to get a curve like this. Okay. Then what do you have? Then you have x of s. Of course, the solution depends on the starting point, no? X of tau, starting point x of tau, y of tau, z of tau. This y of s tau and z of s tau. You see, this forms a surface. I already told you the definition of surface. Okay, in two parametric form. S tau, S and tau are being parameters. Now there is only there is only one place where things can go wrong. That is, suppose this initial curve x of tau, y of tau, what is the direction of x of tau, y of tau, z of tau? In this picture, this is the direction, no? And what is the characteristic direction? Direction of the characteristic curves? PQR. That's what your star says, PQR. The most important thing is this PQ, when a curve has to come out of this point, like this, so that it forms a surface which contains this, these two cannot be in the same direction. Okay? If one goes in this way and the other one should come like this. That's why, when I have drawn like this, characteristic should emanate from the initial curve. Okay? So therefore, what is the condition? What is the geometric condition? This PQ, okay, this should not lie in the direction of x dot y dot. sorry, maybe you call it as x naught, y naught. This is initial curve now. Okay. Dot product with x naught dot y naught dot. That means derivatives. This should be different from 0. Okay. Of course, PQ at x naught, y naught, z naught. This is another geometric requirement. Otherwise, you cannot form surface. You cannot form surface. Okay, maybe the people write it. I write in a different way, which is more rigorous. X naught tau, y naught tau, z naught tau, q of x naught, the same thing. So this x naught dash tau, this is dx naught by d tau, dy naught by d tau. This determinant has to be non-zero. Okay. Otherwise, this they don't come transversely. These characteristic curves. So once you have this, whatever you have here, x of s tau, you write y of s tau. Okay. From this, you can write s and tau in terms of x and y. Okay. Under this assumption, I can write, you write a maybe solution of this am I using small letters or capital letters? Maybe best way would have been to use capital letters. You just take these two functions. Using what is called inverse function theorem, I can write s in terms of x and y locally, tau in terms of x and y. Okay. So once you do this, once you can write s and tau in terms of x and y, you write in a new coordinate system. Write in new coordinate system. Then you simply get z is equal to z of s of xy, xy, tau of xy. Okay, and this is a solution. This is a solution. So this is how you patch this one parameter family of curves, parameterized by tau. Okay, if I fix tau, I get a curve. Okay, so this is one parameter family of curves. One parameter family of curves. Okay, and this one parameter family of curves, it forms a surface under this condition. And that surface is a graph of the function. Z of s of xy, tau of xy. Okay, so this forms a surface if this holds. Okay, and this surface is a graph of a function. This holds. Okay, this is the geometry of quasi-linear Pde. It just starts with a simple observation that PQR is perpendicular to ux uy minus 1. Okay, I have 5 minutes. In that, I'll try to give you an outline of geometry of nonlinear equations. Of course, once you understand this geometry, if you're writing proofs and so on, it's quite simple. It is just a small exercise in analysis. Okay. Suppose you consider the situation where you have this f of x, y, u, p, q equal to 0. Of course, where p equal to ux, q equal to uy. This is a standard notation many textbooks use. Okay. Earlier you had a tangent plane for solution surface. There is a tangent plane attached to it, which contains the line with direction ratios PQR. But here, Q can be written as, of course, we assume that FQ is non-zero. So Q can be written as XYUP. Okay. So you don't have a, you cannot make such kind of statement what you could do it in the case of this. Okay, because earlier you could solve uniquely, you could get that PQR lying on the tangent plane. Now you cannot make such thing. Okay. Instead, what you could do is, what you could do is you have a variety of possibilities for tangent planes. Okay, variety of possibility for tangent planes. So what are they? This z minus z naught is equal to this p into x minus x naught, okay, plus this q, which is a function of all these things, you know, x naught, y naught, z naught. X naught, now this time I write all the things, x naught, y naught, z naught, p of y minus y naught. This is the tangent plane. Okay. Now, as p varies, for every choice of p, you have a tangent plane. Okay. So therefore, you have plenty of tangent planes for plenty of possibilities. Okay. Earlier, you had only one possibility. The tangent plane earlier, it has a fixed line. Okay. This line has direction ratios PQR. Okay. So this tangent plane can move only along this line. Okay. The line is fixed, tangent plane can move like this. Okay. It can only rotate along this line. It doesn't have any flexibility. Whereas here, there is no such line passing through it. It can actually rotate. This plane can rotate without passing through any fixed line. So, and if planes keep rotating, what is the envelope? The envelopes turn out to be cones. Okay, the plane can touch these cones. Okay, so they are called Mauger cones. Earlier, this plane can only rotate around this line. Okay, either like this or like this. Okay, it can only rotate along this line. Now it has more flexibility. Okay. So what you do is, in order to write characteristic equations, you first find what are the generators of this cone, and then once you find it, very easily you can write characteristic equations. Once you write characteristic equations, theory is exactly the same. All that you need to do is you have to just solve x and s and tau in terms of x and y and substitute there. Okay. In nonlinear case, you have this Monge cone, which is an envelope of
हेलो हाँ वो जो बोलने कैसे
tangent planes
हाँ हाँ ठीक है
given in, maybe you call it as
नहीं घर में रहना नहीं कौन भी नहीं रहता घर में
these
कैसा
are called Monge cones. So at every point, earlier you had a tangent plane attached to it.
हाँ
In the
चालू
case
है
of quasi-linear Pde, you have
हाँ
characteristic curves, and characteristic curves have tangent planes attached to it. Okay, with this direction PQ, having line direction PQR. Whereas here, in the case of nonlinear equations, you have a surface, and at every point these cones are attached. Okay, like for fish you have scales, no? For fish on the surface of fish you have scales attached, right? That's how it will be, like this Monge cones. Once you know how to find generator of a cone, okay, or how to find the envelope of family of surfaces, then it's very easy. Envelope means working rule is quite simple. You just differentiate with respect to the parameter and then eliminate the parameter. Okay, so that's it. Once you do it, you get easily characteristic equations. Once you get characteristic equation, it's it is as it just goes along the lines of quasi-linear equation. But the thing is, you may need to do more calculations. You may need to do with clumsy expressions. That's it. Except that, that's nothing. Okay. You have any questions? Any questions?
Yes students if you are having any questions you can ask.
Yes, sir.
You understood everything or you did not follow anything?
Sir, this is what a response we are getting in every lectures also.
No, maybe they are bit timid and they're afraid. Maybe you have to motivate them to not to be afraid. That's it.
Due to online lectures they are not much more responsive.
Okay, that's another thing. Yeah, I'll be happy to answer your questions regarding this or anything other apart from this. If you have any question in PD also, you can ask me. So your questions need not be limited to whatever I spoke today. Yeah, so this is, if you think that I went very fast, you couldn't follow much, that's fine, I don't mind. Or you can, if you have any other question from PDE or ODE, I'll be happy to answer. When do you learn PDE? In which semester? Students?
Sir, it is at 4th semester for the students.
It is in the 4th semester.
Yes, sir.
They are learning now. Some batch, some students are learning now. Is it?
They have completed semester 3 and some students for semester 1. So, but PD has been already introduced to them at BSc level.
Okay, okay. Yeah, in BSc they would have learned then Lagrange method. You would have learned, right? Dx by p, dy by q. That thing.
Some of the introduction was there at BSc.
Okay, okay. Yeah. So ongoing course is not there, no, for 4th semester.
Yeah, sir. We just now completed semester 3 and exams will be there in the next, and then we'll start semester 4.
Okay, okay. Maybe that's why they are not asking many questions. Yeah, I understand. So then ODE, we have anything in ODE?
Yes, ODE is there at semester 1. They can ask.
Oh, okay. Yeah. If you have any questions in ODE, you can ask me then. Or if you have shyness in asking questions, you can write to me if you have any questions. My email ID is suman.hcu@gmail.com. Okay. See, many times students have this inhibition that what others would think if I ask such a simple question. They would think it that way. Oh, it is so simple, all others may know answer of it. Only I may not know answer of it. If I ask this question, such a simple question, other students will think bad about them and so on. No, it's not like that. No question is simple. And no question is stupid. You can have stupid answers by teachers, but you cannot have stupid questions by students. Okay. Yeah, fine. So if there are no questions, I'll stop. Huh?
Yes.
Thank you very much.
I will request Vishal Kori sir for the vote of thanks.
Yes, ma'am. I'm audible?
Yes, sir, you are audible.
Okay, thank you, ma'am. A very good afternoon to all. I would like to present the vote of thanks for a national webinar on a partial differential equation geometric approach organized by Department of Mathematics, School of Computational Sciences, Punyashlok Ahilyadevi Holkar, Solapur University, Solapur. I would like to thank our beloved Vice Chancellor, Dr. Mrunalini Fadnavis ma'am, for giving a permission to organize this event. I would like to thank our resource person, Dr. T. Suman Kumar sir, for accepting our invitation and giving such a nice lecture on a geometric approach of a PDE. I would like to thank our director of the school and HOD, Dr. J.D. Mashale ma'am, for organizing this event. I would like to thank all the staff members, teachers, students and participants. Once again, I thank one and all present here. Thank you, sir. Over to you, ma'am.
Okay.
Okay, so shall I?
Yes,
log
sir.
out? Okay.
Thank you, sir.
Yeah.
Yes, students, you have an instruction that you have to join the next session at 3. Madam may start the session at 3:30. Okay.